My name is Agustina. I'm a PhD student in Buenos Aires. I'm from the Buenos Aires Logic Group. These are all my affiliations that I have to declare. And thanks PLEXUS for bringing me here to the European Union. Yes. So this, the plan of my thesis was substructural theories of vagueness. The first three keywords I presented were these: substructural logics, meta-inferences, and vagueness. Okay, let's see how all of these comes together. First one, so substructural logics, let's take the naive definition that Damian is tearing apart. Usually are taken as synonym with non-Tarskian logics. So what's a Tarskian consequence relation? Well, here I put the definition by Scott, which is the same, but extended to multiple conclusions. So a Tarskian consequence relation in a language or for a language is a binary relation between finite sets of formulas that satisfy the following properties. So reflexivity, every formula implies itself. Monotonicity, you can add, if something is valid, you can add extra things to the premises and the conclusions and it will still be valid. And transitivity, well, this is just cat, but encoded in this property, right? And it's closed under uniform substitution. Also, it's not here, but non-contractive logics are usually taken also to be substructural logic, so I wrote contraction as well. Great. Now, meta-inferences. What are meta-inferences? In the most basic level, they are inferences between inferences. Of course, this can be generalized. So this would be level 2 meta-inferences. But on the level 3, we would have, for example, this and a line between these two, let's say. I almost... And it's very easy to see how this relates to the previous slide, right? Because these structural properties, these particular meta-inferences or transitions between inferences are encoding these structural properties. So both things are clearly related. So when working with substructural logics, one is most likely to find this literature along the way. Next. Great. So, derived interests that come from these lines of work. First, studying sequence calculus, because in a sequence calculus, the structural properties are explicit rules, and one can see precisely the transitions between inferences. So it's like it's exactly the thing, the kind of tool that allows you to work with meta-inferences. And a second derived interest is meta-inferential logics. So logics where the focus is not put on what inferences are valid, but on what meta-inferences are valid. And it's very easy to see that one can generalize this, again, to the infinite level. So have omega logics, let's say, or yes. So this, I want to present something more along these lines. The sequence calculus part, it's something that I'm working alongside Martina mainly, so I will leave that to her. And this is something that I'm working with Ailén, Joaquín, Bruno, and Ariel, who are colleagues in Buenos Aires. So, I'm going to present a meta-inferential tableau. It's a method for generating a tableau system for any n-valued finitely valued n-valued logic. So if once we have a inferential tableau, we can add these meta-inferential rules and obtain a meta-inferential calculus for logics, for example, the strong Kleene ones, which are the most well-known ones, but also weak Kleene and 4-valued, 5-valued, anything that has a truth table, not necessarily deterministic, but that has a truth table. And we have a program to test it. You can enter this page. Please don't share it. Don't share the link because it's not ready. But here you have.
I thought it was. I know.
Here, meta.
Let me show you just to show you.
calculator dot modify on app, and there you have the instructions on how exactly you can use it. This is the outline of the talk here. And so the idea is this. We have a propositional language, the standard binary connectives, and the unary connective for negation. We use this arrow to separate the premises and the conclusions, and we indicate the level on each case. So for formulas, we will be using this uppercase Latin. For inferences, we can use either this or this. Meta inferences, we can use this right here. And in general, for meta inferences of levels up bigger than 2, we will use this, but always remember that these are just a level below. Okay, perfect. Let B be a set of truth values. We will define a standard in the following way. So a standard is just a subset of the set of truth values. And since we will be working, as an example, with the strong linear evaluations, we will be focusing on these two particularly. And T. 1.5. Yes. Says that if something is a level n standard, then its complement, it's also a standard of the same level. And if these two things have standards of the same level, then concatenating them gives us a standard of one level above. No, it's fine. Now, evaluation is a function from formulas to the set of truth values. Formula satisfaction is defined like this. So evaluation, let's say, S satisfies a formula if the evaluation of A is 1, since that is S. And meta-inference satisfaction is defined in the following way. So evaluation XY satisfies a inference or a meta-inference if and only if the evaluation satisfies every premise according to the standard X, then it satisfies every conclusion some conclusion according to the standard Y. So another way of saying this is that no evaluation is a counterexample to it. This just states the same thing. So this is for the formula level. For the inference level, we have, let's say, SS, TT, TS, ST, and then from the following level, we have this, right? These are 16 in total. The important point here is that this can be mixed, so mixed standards. This, in the case when we have the strong linear evaluations, this equals K3, this equals LP. And in the case of sequence, we can evaluate the top one according to, let's say, K3, and the one below according to LP, for example. Okay. An inference is valid in BXY if every evaluation satisfies it. Well, this is local validity. I will make a brief comment at the end about global validity.
What's local validity?
It means that
the level of your logic?
It means that we are looking at every preservation of satisfaction, but in every evaluation. So we're not saying that, for example, in this case, right? We have, let's say, P, let's say P and Q. We say that every evaluation that confirms this, so it's not a counterexample to it, also satisfies it. It's different from saying that if this is valid, then this is valid, because this is not valid. This is not this is not true in every evaluation, but in every evaluation that makes this true, it also makes this true.
Okay.
That's okay. Okay, so a meta-inference of level 2 is valid in this logic if and only if every evaluation that satisfies the premises according to the logic 1, then it also satisfies some conclusion according to the second logic. Well, and this can be generalized for every level, but let's keep it at level 2 for simplicity. Okay. This is like the semantics of meta-inferential logics. Let's present now the proof system. We assume, let's see what it says here. Well, I won't be talking about hierarchies in this presentation because I think it's too much. But we will be working or presenting this for the set framework. So multiple conclusions, including in the meta-level case, since this topic was brought on today. Okay. Nodes have this form where A is either a formula or a meta-inference, and X is a standard of the according level. We have two kinds of rules, the general rules and the particular rules. The general rules are the ones that allow us to extend or obtain a meta-inferential calculus for any particular inferential logic that has a Tableau system. So we will exemplify this with the case of strong cleaning, but nothing in particular hangs on this choice. So it can be used, this same method, to other evaluations. Okay, we start like every tree starts like this. Assume we want to prove that a meta-inference is valid in a logic xy of level n. Then we start like this, assuming that it is not. So this is what this label means. Where x and y are the standards of these ones, right? Are the labels corresponding to these two logics. Great. Now the first one is the, let's say, inference dissatisfaction. So what happens if a meta-inference is invalid? That means that every one of the premises is satisfied by this, or has a evaluation that satisfies it according to the X standard, but does not satisfy any of the conclusions according to the Y standard. And then we have the rule inf1, which is the opposite, is inference satisfaction. So if a meta-inference is locally valid, that means that either, let's see, there is a evaluation such that it does not satisfy the premises, one of the premises, or satisfies one of the conclusions.
Sorry.
Yes.
So you're going from satisfaction claims to satisfaction claims.
Yes.
Reasoning. Okay.
Yes.
Okay.
Now these are rules for transforming the labels. Complement of a standard, I think, is pretty self-explanatory. Next one. Intersection, also I think pretty self-explanatory. So the intersection of S and T would give us 1, right?
Wait, sorry, can you go one step?
Yes.
But this only works for level, this formula, okay, sorry.
Yes, maybe one thing I should mention is that the intersection has to be done in labels of the same level, right? So.
Yeah, of course, but this is formula, so sorry.
Hey, one question.
Yes.
So that A is not X satisfied does not mean that A is satisfied by the complement, is it?
No, for inferences, this is only for formulas.
Okay.
If A is not in the subset X, it has to be in the complement.
Thank you.
Singletons. This rule is the worst because when using the computer, the program, it branches a lot. So
I have some examples here.
yes, it branches.
It's very nice.
It branches a lot, so it makes the calculus very inefficient. There are ways around this, but none that are like philosophically nice. Okay. So, as I mentioned, we wanted to present this system as a general method for generating meta-inferential calculus for any logic that meets certain requirements, for example, being finitely valued, having truth tables, let's say. So, this is the way in which to generate the rules for the connectives, in particular, the rules that are going to determine the logic, inferential logic we're working with. It's just, this is, the only thing it's saying is that these rules, you have one for each, let's say, truth value, and for each connective that just replicates what the truth table said. Next. This will be our example, the strong linear truth tables. I don't know what else to show you. These are the rules. They are not exactly the ones generated by this process, but these are equivalent. We are currently looking for a method for streamlining rules. So if you have any recommendations, that means just to avoid unnecessary repetitions and making it so that the rules are as informative as possible, but not overly informative, right? Next. Well, what is the winning strategy? The strategy for proving something here. First, we apply all the general rules for meta-inferences and labels, and then once we are in the formula level, we apply the particular rules for the connectives, and lastly, the rules for labels. A branch in a tree is closed if a formula labeled with the empty set occurs in it, otherwise it is open. A branch in a tree is closed if a node of the form that has the empty sequence, let's say, appears in it. This rule is added in the case for working with the set framework for reasons of completeness. A tree is closed if and only if every branch is closed, otherwise it's open. And given an open branch, we can build a counter model off of it. Okay. Well, let's give an example. So this is an inference we can call meta explosion. Meta explosion is valid in this logic. This logic, in fact, is the same as classical logic. The logic TS-ST. For meta-inferences up until this level. So this is a case where the tree closes. Let's see a failed proof attempt.
Oh no, I want to look at the proof.
Sorry. Okay.
I want to understand what's doing
Okay.
in a concrete
This is-
way, please.
Sorry, I'm kind of rushing because I have a lot of slides and very little
Please,
time.
I'm trying to understand concretely how this works.
Okay, so we want to prove that this meta-inference is valid in the logic TS-ST. So the logic that evaluates the inferences on the premise side with the logic TS and the inferences on the conclusion side with the logic ST, which is classical logic at the inferential level. We start assuming that it doesn't.
Okay.
Then we apply the rule called inf0, so inference dissatisfaction. That means that this is satisfied by evaluation according to the TS standard, but not according to the ST standard. Now, let's see. Here I used the same rule again, but notice that there are no premises. So here I only have one line instead of two. And in this case, I also applied the rule for inf1, so inference satisfaction. In this case, that means that the conclusion is there are no branches in this case because this is empty and this is just one formula, so it means that if this is valid in TS, it's because it's S satisfied. This is the rule for transforming this label. So this is the same as saying that
Q is 0.
yes, it's 0. In this case, I used the rule for the conjunction. So since it's true, it means that both are true. Then the rule for the negation, and here the intersection, right? To obtain the empty set. Okay. In this case, so in this case is it doesn't close, and it's okay. It's what we want. We want it to. It would be wrong if it closed the tree here. So and it allows us to have a counterexample. So in this case, let's say. We have this. The counterexample is given by the case where this is 1/2, 1/2. So this is valid in the ST logic, right? Because it is T satisfied, but in the case of Q, we have that it is false, right here. So this is the counterexample in this case. Okay, some comparisons to, this is not the first meta-inferential proof system. So meta-inferential logics have been mostly studied from a semantic point of view. There have been some other proof theoretic presentations. Let's see, we have Roffé and Pailos present n-sided sequence calculi. We also have the special edition on the, that Paul and Eduardo were editors of, where also Pablo presented n-sided sequence calculus, but only for classical logic and strong cleaning, right? In Cobreros, Tranquila and La Rosa, this one is the, I should have put the date, this is the anti-satisfaction one, right? They also present Tableau, but only for strong cleaning with the inferential logics of the first level. So the main advantage of this presentation that we're giving is that it's completely general. It provides general rules independent of the set of evaluations or the schema we're working on. It does not add new vocabulary to the object language, and it's enough for with having a single matrix characterizing a logic. Can be non-deterministic also. So, okay. Side note on hierarchies. Usually, the people working on this literature have defined what are called hierarchies of meta-inferential logics. Damian particularly here presented the BPS paper. Yes, but I will not be discussing this here, but we have also lowering and lifting rules for defining the hierarchy. Okay. Global validity. Global validity is kind of hard to give a calculus for globally valid meta-inferences. This is an attempt. So a meta-inference is globally valid basically at level, let's say at level 2, if there is preservation of validity or preservation of derivability. So in the local case, we had that if every evaluation that satisfied this. In the case of global validity, we have that if every evaluation satisfies this, then every evaluation also satisfies this. So that if this is valid, then this is valid. global validity is more general than local validity, so everything that's locally valid is globally valid, not the other way around. Yes.
That's not true.
It's the other way around.
Sorry, I'm kind of tired.
No, it's neither way around.
No,
At level 2, everything which is locally valid is globally valid.
Yes.
At higher levels, they're incomparable to each
Yes,
other.
I have notes. I have notes on the other levels, but let's wait for them. So we have this rule and these kind of lines now. These lines help us keep track of some subtrees. So what we want to say is that for this meta-inference to be globally valid, that means that either one of the premises is invalid or one of the conclusions is valid, which is something that it's very hard to prove with Tableau because, for example, this would be globally valid in, let's say, the logic X, Y, W, C, P, let's say R implies S. So it's kind of hard to close a tree when you have all of these appearing on the same branch or in different branches. Okay. Closing trees. So a meta-inference is globally XY valid if and only if either the tree for the dotted lines, so that's one of those subtrees remains open once we terminated applying all of these of the rules, or if one of the normal lines is closed under the normal, the previously given conditions. So let me give an example first. Can you go back to inf G? Yes. So let's write an example of this. I hope it's clear. Let's see. And let's put this, it doesn't matter really. So in this case, we would do something like this. I think it's like this, and okay, so now the idea is to use
I think it's in the first branch without the hat, the x1.
yes, it's because I want to use inf 0, right? Exactly.
Let's see.
Okay, so I want to do this, like extend instead of branch here. So it would be and Q.
Okay.
This will also remain open, but the important case is that this one remains open. So the subtree that has this as its root, so then the tree closes automatically. That's the general idea. I don't know if it works. It's a conjecture, conjetura at this point.
So it is as if you, like in the meta-inference, you just make a tree for the premise, right?
Yes.
If it
Anyway,
closes
No,
one
it's
or
not
the other,
exactly like that. It depends,
Sorry.
as Bas said, it depends. This is at level.
Yeah, this is level
Yes,
two.
but if you're in upper levels, then the how to proceed next is not so obvious.
Yeah, I guess.
Okay. Okay, you can also have a calculus for anti-validities. So anti-validities in this literature are known as inferences that have in which every evaluation is a counterexample to it. So in classical logic, it would be something like a tautology implying a contradiction. That would have a counter model. Every evaluation would be a counter model. And in this case, what we would do is instead of starting the tree with inf 0, we will start with inf 1. Okay, that's all I'm working on regarding meta-inferential logics.
It is a lot.
It is a lot, because we are a lot of people also. But now there is like one thing that I didn't touch on, which is how all of this applies to the vagueness case. So I wanted to maybe see some examples of how substructural logics apply to are applied as solutions to the Sorites paradox. Just to close. Okay, so vague predicates are usually found in this form in natural language. They are gradual adjectives, so child, red, rich, tall, or scalar nouns such as a bunch of x, whatever x is. They don't have an exact definition, but one can characterize them as lacking sharp boundaries. So, for example, there is not one last second that one is a child, or one last penny that makes you rich or poor, let's say. They have borderline cases. So, for example, there are people who are neither clearly tall, neither clearly not tall, and they are Sorites susceptible, which means that they are susceptible to Sorites paradoxes, which are arguments of this form. Sorites paradoxes have a particular characteristic, unlike semantic paradoxes, that they have several forms in which they appear on and several connectives. So what this says is that if something in a series, in an order series, has a property, then the next one has it, and the first one clearly has that property and the last one clearly does not, then a contradiction ensues. Let's put an example. So somebody who is this much days of age, so 5 years old, is a child. Is clearly a child. Like, there's no contesting that. But it's somebody that has n days of age is a child. Then somebody who has one extra day is also a child, because these predicates lack sharp boundaries, right? This is called a tolerance principle. It's a kind of principle that characterizes the meaning of vague predicates. Then somebody who is also who is this much days of age, so 50 years old, is clearly not a child. But all of this in classical logic and in almost any logic follows a contradiction from this. Let's see how some interesting solutions to this. So I put the Sardini quote, but an ST example, just to have variety. So
ST is actually a particular case of Sardini's approach. So.
So the idea here is how do we relate transitivity and vagueness? Well, it seems to be kind of obvious, right? Because you're kind of like moving in a series, and you're starting with something that clearly has a property, something that at the end doesn't. So at some point it seems that transitivity would fail. Or, maybe somebody that has this much centimeters tall, and somebody who has one extra millimeter, let's say, is also tall, but maybe, no, it had to be the other way around. Not tall, but maybe 2 centimeters or 2 millimeters can make a difference. Well, this is an example of a non-monotonic solution to the Sorites paradox, and this is an example of why it would fail, right? So in a non-monotonic view of vagueness, we can accept the validity of n-fold tolerance, so all of these series, and conclude that the final one also has this property, but the problem arises when such a conclusion is maintained in the face of countervailing evidence. So in this case, we add new information that now serves to create a counterexample to this. Okay. Contraction and vagueness, there are some, here the relation is not so clear, but there are a lot of non-contractive solutions to the Sorites paradox. This could be one, for example. The idea here is that premises should repeat as many times as they are used in a derivation, otherwise the inference is not valid. The tolerance principle works as some sort of inferential resource, and you can't appeal to that resource indefinitely, because that one is the thing that leads to the let's say, absurd conclusion. This is just an example. Reflexivity and vagueness, I have no clue. The closest thing I found is this understanding of vagueness as conflation. So conflation is an epistemic phenomenon in which we take two things to be the same one. And basically, David Ripley here has a solution to the Sorites paradox where it's not exactly non-reflexive, but I think it has like a non-reflexive tint to it. Because basically what he means is that we are always talking in a conflated language. So in a language where we conflate things, objects, but also propositions. So if we unconflate them, maybe we can get two different things. Yes, so that is all. Yes, please.
Thank you very much. No, it's a lot, and it is good because you have you have a lot of things for your PhD, and I'm pretty sure that you will complete. You can complete a couple of PhDs on. So, about so you mentioned several things about the three rules. So I think in the spirit of your project is keeping generality for the number of values. And the kind of schemas that you use, and the levels you take in the meta-inference step. This is in sort of intention, I wouldn't say incompatible, but intention with the simplicity of rules. So for example, if you go for a weak-clean scheme, you will get very messy rules. If you just
I have them, please. Please show the appendix. Here.
Oh, that's with cleanness quite okay.
No, I know what you mean. The infectious logics are very difficult to give a Tableau system for, but the thing that makes it work here is the fact that it branches. It doesn't appear on the same branch. So here this works. In other systems you have to act like a classicality label or something.
No, I think this is as simple as you can you can get with cleanness. But the idea is that if you are thinking about the generality of your approach in order to say, okay, let's introduce more truth values, and we'll have an algorithm to write the tree rule for any matrix. The general algorithmic will give you super messy rules, and I don't know at least of there are some hints that you can apply in general in order from these rules some simplifications. So if they satisfy some properties, you can get less branches.
Yes.
But I don't think there is a general approach to get the shortest.
Yes, the streamlined rules. Okay, so we have.
There is a paper on this. I will send to you.
Please. So these ones we obtained following the method by Walter Carnielli, but we're actually looking on another one given by Bass, Vermeulen, and Weber. Because that one in particular has these streamlining directives, let's say, that allow you to shorten the rules.
I just want to make a comment because when you said that I can't find my truth values, I was just thinking I can define them as sets, and then I have no deterministic systems, and then you are lost. Sorry, because I can't really do much. It's actually very hard even doing those things by hand. So I think you need to be very careful. And also I should find, obviously not in your computer system, but you are actually providing a theory. And if you are providing a theory, you could go with infinite sets of values. And then again, I don't think it works. And I think that method by Carnielli and actually the resolution systems or Tableau extraction that's given by the people in Vienna is just working on finitely many values. So in my work in a system, because you are actually just entering finitely many values and not anything that's more general, and if you try try to do that for more values than
Mhm.
or more general truth sets, then I don't think we got a method from that.
Because as far as I know, Carnielli's method don't take into account any structure that you might have on the set of values.
No, you need a truth
So,
table.
yeah.
So you need a truth table, and you don't get a truth table from any set of truth
Mhm.
values.
Okay, so determining the scope is also like part
It's
of
a
the.
good thing. It's always a good thing. Yes.
Can I say something about the global validity? I
Please.
tend to think that so conceptually the issue shouldn't be very difficult. Is my guess. I didn't get into it, but I tend to see global validity claims about meta inferences. So you can look at them as disjunctions about validity inferences. So each time at the level of meta inferences level 2, all you have to do is, you have a method. It's not very nice. That's the problem. But there is a very simple method, which is, okay, write the tree for the inference in the premise. If it closes, go to the second.
Mhm.
No, if it's open, you are done. The inference is valid. If it closes, then you have to move to the second, then write a tree. And I suppose that for higher level inferences, you will have just to put an order in which you have to check whether some of the key inferences is valid, to stop searching,
Mhm.
or to keep writing trees. It's not very nice.
The notes on global validity I added later because I know Bas was coming and he was going to make a comment about it. So yes, I was. So this is like the best crowd because maybe you two and Paula are like the people most knowledgeable about this. So I think this is great.
I actually also wanted to ask, just if you could show again
Yes,
what your brochure was.
I have. No, in the appendix, Dami,
Sí.
I have some slides on global validity, particularly how to follow for upper levels. So
Wow.
the idea for what I understood from the brief talk you gave in Buenos Aires is that for any level of meta inference you have n validity notions that you can define. So let's look at two examples for the case when we up one level. For level 3. In this case, we can understand, let's say, global validity as preservation of global validity. So in this case, what you would do to prove that a meta inference is preserving global validity or something like that is apply the rule twice. So inf g. I don't know if the labels are right. I didn't check the slides, so they might be a bit off, but this is the general idea. The next one. But we can also maybe want to understand it as preservation of local validity, in which case we would do the inf global rule and then follow with the inf zero case. So the ones we use to prove local validity. This part is the conjectural part. I don't have it. I have proofs that the other part of the system are complete, but not this. So
I mean, this should work because if you want to use global validity understood as preservation of global validity all the way up, which is what I think you should do, then for any level n inference, you apply this inference. What is it called? Inf g.
yes.
Which
Dami, can you go to inf g? Thing. No, inf g is at the yes. Sorry.
Sí, sí, no, no.
Yes.
yeah, so you apply this like n many times until you have
Yes.
a level 1 inference, and then you just use the proof system to determine the regular validity of all of those inferences, and then but I think that's
That's
essentially
my
the procedure
intuition,
that
yes.
Paolo
Yes.
was describing, which is going to blow up a lot at higher levels, I think. And so now I have one more question about this. So why are the labels
I have
all
no idea. I'm trying to.
Yeah,
I'm
because
trying
this
to
should
remember.
in order to show that this is not globally valid, you should either show that, well, you need to
No,
show both that all the premises
this is
are
the case for-
valid.
See, I see the point. So this would could be read as saying that it's not globally valid, but it should be it shouldn't be with the overline.
the overline
And this
should-
here depends on the level how you proceed or what you choose to do. So this is also like a work in progress. The hat.
But I was question. So in this case, you are trying to determine whether this is globally valid,
Yes.
right? Okay, so the Tableau, you assume it is not. That's more or less what you do. You assume it is not globally valid, or you are actually assuming that it is, and then trying. Okay, you're assuming that it is.
We are assuming that it is because
Okay.
but here we're proceeding in the refutational way in this in this
Sí.
step
Sí.
because we want to these branches for them to close we have to assume that they are not satisfied by the evaluation according to the standard specified. These ones are the strange ones, let's say.
Wait, sorry, what do you mean?
So here we proceed, when this is level 2 here we proceed with the inf 0, with the ones that
Yeah.
we were used to prove local validity. But, well, in these ones here, if this is 2 also, we proceed in that way. The case for n's higher than 2 is to be determined according to what you want to prove. So if you want to prove that it's global valid, global local valid, or something like that, in that case the labels would have to change.
But I don't think it's the labels that have to change. It's which rules you apply next, right?
Because if in the case of if I want to prove that something is globally valid, I have to also have no, that's why this is like this, I think, because in the other case I gave this presentation months ago. I don't know if you can tell. No, you're right. I think they are right? The labels.
Well, I think so. If the label at the root says that this is not valid in the standard XY, so then you have to prove that all the premises are valid and none of the conclusions are. So then the bars above the X's should be gone. No?
Yes.
Right.
Yes.
Okay.
Okay. I don't know if I should maybe, I don't know, I think with this is enough. I was also maybe thinking of having a if 1, if 0, but with the global validity case, but I don't think it's going to add anything.
Okay. Thank you very much.